This is the video for Chapter 4, Part 2. Alright, so in our last video we talked about scatter diagrams, and we can check that off. Now we're going to talk about properties of that linear correlation coefficient, which we're going to call R. So how do we tell if there is a relationship and how strong that relationship is between two variables? Well, we use the linear correlation coefficient, which we call R. And previously we had a graph that looked kind of like this, and we saw that, yeah, more or less, there's somewhat of a relationship here, but how strong is it? Is it a positive relationship, a negative relationship, whatever? So what we end up doing is we try to figure out, based on what we know about our data, we calculate this variable R. Now, there is a formula to calculate R, but as we've been doing, we will use our calculators, not the formula. I will show you the formula, but first let's look at those properties. Our first property is that a linear correlation coefficient is always between -1 and +1. And of course, symbolically in the math world, we love being able to write things a little more concisely. And so that's what this next little part is. So -1 less than or equal to R less than or equal to 1. That basically just saying between. R literally here is between these two numbers. It's in the middle of -1 and 1. So what are these extremes? Well, if you remember from probability, we said probability always has to be between 0 and 1. We couldn't have negative numbers with probability. We can have negative numbers with correlation. And I will, in the next two properties that we talk about, we'll see what that really means. But with probability, a 0 probability meant that there's no way it was going to happen. And a 1 probability meant that it was certain to happen. So impossible and certainty, those were our two extremes. So what are our two extremes when we're dealing with a linear correlation coefficient? Well, the first extreme, the positive one, if R is equal to +1, then a perfect positive linear relationship exists between the two variables. So what would this mean? Well, this basically means that our data makes a line, a perfect line, not almost a line, but like, for example, if we took data and we let X be, let's see, so if we let X equal the diameter of a circle, and we let Y equal the circumference, then that would have a perfectly R equals 1 positive linear relationship, because we know the diameter and circumference are related. If we use X and Y, which we would not normally do with circumference and diameter because we would use a capital C and a D, but we would say that our circumference is equal to pi times the diameter. And that would be our perfect linear relationship between those two variables. That would happen. All right, so that's our example that we would use to see a perfectly I don't know why this is not letting me, there we go. Wouldn't let me erase. Okay, and so that's our second property. Our third property is the opposite. So what if R is -1? Well, if R is -1, then, there we go, a perfect negative linear relation exists between the two variables. And so this would be something where our line, our data points would fall perfectly in a line, and the line would have a negative slope, basically. So whereas for the circumference and the diameter, as the diameter increases, circumference increases. That's a positive relationship. They both go up. Then for a -1 association, we would have, as our X increases, that's a horrible axis, but we'll just pretend like it's okay. As my X increases, so as I go further along the X axis, my Y values actually decrease. And they do so in a perfect line that I could connect straight line through all the points. That's if it's exactly -1. All right, so our next property, there are 8 of these, by the way, so we've got 2 more slides that we'll go through. Our next property, property number 4, is just saying what happens when we get close to one of these extremes. And so the closer R is to +1, the stronger evidence we have that there's a positive association between the two variables. And of course, the opposite will be true. I don't know if it's the opposite. It's the negative, but it's still stronger. So if it's closer, the closer it is to -1, the stronger our evidence is that there's a negative association. So we've got to be really careful because we're used to going from strong evidence, and then if we go to the opposite side, we have weak evidence. Well, that's not how this works. So our evidence is strong on both endpoints. If we're at or close to -1 versus if we're at or close to +1. Those are both give us a strong indication that there's a relationship. It's just if that relationship is positive or negative. When we have little evidence of a relationship, it's because we have an R value that's close to 0. But we have to be careful because this evidence is only of a linear relationship. So the value of R close to 0 does not mean no relationship, but just no linear relationship. So again, that's very, very important. And I've got a picture that will help kind of show like why we want to be careful of that. Because we could get a value of very close to 0 for R, but it actually have a very strong relationship between the two, but it's just non-linear. So let's take a look at some of those examples. All right, so we still have 2 more properties, but let's look at some images first. So our second and third properties said that if we had exactly 1 or exactly -1, then we had a perfect linear relationship. So here are 2 graphs that show that. So these, let me label them. So this first one in the top would be something where we have an R equal to 1. That's a perfect positive linear relationship. And similarly here, we have an R equal to -1. So exactly 1, -1. It's perfect linear relationship. If I drew a line, I could draw a line through every single point. All right, so that was property 2. Let me mark that too. So we'll say just number 2. This one was number 3. All right, our fourth property said that the closer R is to -1, the stronger the evidence is of a positive relationship. And the closer it is to -1, the stronger the evidence is of a negative relationship. So we've got a couple of graphs to show that. So here, let me go back to my pen. So this this next graph here would have an R of maybe, let me not put equals. Let me actually use approximately. So there we go. Well, let's start over. So R is approximately, maybe, I don't know, 0.9. Pretty strong relationship there. We can definitely tell that there's a pattern. If I draw a straight line through there, I'm not going to hit every single point, but all the points are going to be pretty close. This next one might be, about, I don't know, maybe 0.4 or 0.5. So roughly you can tell because there are some voids. And when I say voids, I mean like empty spaces. So I can see that there's like down here's a void and up here there aren't any dots. And so I can tell that this is a positive relationship still. It's just not quite as tight together. The points aren't all as close to what that line might look like. So if I were to think about, where that line might be, I might have a line going up through there. And so those points aren't quite as close as if they were going through that data. So that is saying, the closer I am to 1, the closer I am to being, the stronger the evidence I have. So these two together, you put a box around them, represent our fourth property. And then our stronger evidence to the negative. Now, these are they're not exactly the same graph, just flipped around, but they're very, very close. So, this is going to be an R that's very close to negative 0.9. And our last one here that we can see is probably going to be really close to like a negative 0.4 or a negative 0.5. That looks a little more spread out than the top one. So we might say R is approximately negative 0.4. And so together, these two represent our fifth property. And then our last one that we just talked about was that when we're close to 0, there's little to no evidence of a linear relationship. So not no relationship. Please be careful with that. You can get in trouble by trying to say there's no relationship. So both of these graphs, both of these data sets, would likely have an R close to 0. So but hopefully you would agree that whereas the first graph on the bottom row that was all spread out, that, yeah, I could probably say that there's not really any relationship between those two things. But if I look at this last graph, I have a very, very defined relationship here. It's just not a line. That's more like a parabola. And in fact, if this were an in-depth stats course that were maybe, like a senior level stats course, we might talk about doing quadratic regression rather than just linear regression. But we aren't, so you don't have to worry about that. But just know that this is non-linear. So there's no linear relationship, but there is a non-linear relationship. So we've got to be very, very careful about that R being close to 0. Not no relationship, no linear relationship. All right, and then our last two properties of linear correlation coefficient. Number 7 is that the linear correlation coefficient is a unitless measure of association. So our X will have a unit, our Y will have units, our slope will have units, our y-intercept will have units, but R does not. R is unitless. The reason for this is because if you look at the formula that was used in the interactive assignment, we do not need to use that formula, I promise. But the formula actually isn't that bad. It's, if you look at it, it's simply taking the z-score for the X and the z-score for the Y for a particular ordered pair, with the mean of the X's, the mean of the Y's, standard deviation of the X's, standard deviation of the Y's, and then we're multiplying those two numbers together, so multiplying two z-scores that we have, and then we're dividing by n minus 1. So the z-scores, we've calculated those before. The calculation is not a difficult calculation, it's just cumbersome for when we have lots and lots of values. But when we do that, think about what we have. So let me see if I can pull that up really quick just to explain. Okay, so just so I can point to things, here's our formula. Now, again, we do not need to use this formula for calculations. I just want you to see what's going to happen. So our X value has a unit, and the standard deviation always has the same unit. So my units would cancel for my X's. Well, Y's are just another value. So my Y values and their standard deviation, those units are going to cancel. So I have no units on top. N minus 1 is just how many people I have in my sample. So I'm going to have no units at all for any of this. So that's what happens to our units. Our units get canceled out completely. Okay. All right, and then our last property is that the correlation coefficient is not resistant. So do you remember what resistant means? Hopefully you do. So this was back in chapter 3. We talked about a resistant measure was one that was not affected by outliers. So if our correlation coefficient is not resistant, means that it is affected by outliers or extreme values. So an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. What we might see is it's very possible to have data that looks pretty much like what we expect, and then you have this one point. And maybe it's not an outlier in and of itself for the x's, and it's not an outlier in and of itself for the y's, but together it's far off from the overall pattern. So it may not be just an extreme value, but it could be outside of kind of this bubble that we're allowing. So we say, oh, you know, most of our data is here, and then, oh, I have this guy. That's going to change my R value from being, you know, pretty high, maybe in the 0.7 to 0.8 range, if I just had the dots that I have shaded with gray, to possibly like a 0.2, which is really close to 0, or even lower, depending on how far away that point is, if we add in that red point. And so we look for those things. We want to make sure that we understand if those exist.